Hello everyone. In this presentation, I will tackle the challenging problem of learning temporally consistent video segmentations. My name is Aaron Azulay, and I am a researcher at Lightrix. This work is a collaboration with Tavi Alperin, Orestes Van Soz, Nadav Bernstein, and Ophir Bibi. First, let's define our problem. We assume that we have access to a model that was pre-trained on images of some domain, and we want to transfer this model to the corresponding video domain. We also assume that there are no dense video annotations for our video domain. This is a reasonable assumption, as video labeling is very labor-intensive. The naive approach is to do a frame-by-frame inference using the available trained model. This will usually create highly jittery and inconsistent segmentation masks. This inconsistency is a deal breaker for applications like background removal and object-specific effects. For these applications, a less accurate but stable solution, illustrated by the left dartboard, provides a better user experience than a more accurate but inconsistent solution, which is illustrated by the large spread on the right. This video is a typical example of the problem. The top video is a frame-by-frame segmentation using an off-the-shelf model. The main reason for such temporal inconsistencies is that segmentation tasks are not precisely defined. They are defined by the training set labels. It is often the case that different annotators disagree on what pixels should or shouldn't be segmented, and the learning model can receive mixed signals. For that reason, achieving consistency in video without access to temporal information is possible only in simple domains with human consensus about every pixel. Our method leverages temporal information to achieve a more consistent result. The input is n images and n masks from an image segmentation model. We pass them through encoders and learn multi-input and multi-output decoder. The learning loss has a data term and a consistency term. The data term prevents this architecture from converging to a trivial solution and is making sure that the output masks are not too far from the original masks. The consistency term is an improved version of the flow-based consistency measure that is often used in the blind temporal consistency literature. It is essentially comparing a mask in time j to a warp version of mask in time I. The warp is defined by the flow map, and the loss is computed only on non-occluded areas. We found that object size is positively correlated with the vanilla flow-based consistency loss. Perceptually, inconsistency in small objects can be as disruptive as in larger objects. We improve this popular flow-based consistency loss by normalizing it by the number of object boundary pixels. Indeed, our user study shows that the normalized measure is better correlated with human judgment of temporal consistency. Indeed, using our loss, our method can improve temporal consistency with a minimal sacrifice of the quality of segmentation. Here is one more example. Here we compare to Eilersen et al., which added a loss that enforces transformation invariance in an artificial setting. We also compared our method to the simplest baseline of temporally smoothing the segmentation masks. Notice that in this clip, the dogs are moving relatively quickly and thus smoothing is inadequate. We also show that training with larger temporal context is better, both in terms of accuracy and consistency. However, it comes with a computational cost. Here is the performance with an increasing number of inputs. Notice that the output of our method is not perfect and is inherently limited by the quality of the input masks. Intuitively, if an object part is segmented in most of the frames, the optical flow will make sure that the segmentations will be propagated also to the frames where this part isn't segmented. For more details and questions, you are welcome to read the paper and visit our poster.